So folks, the next example that we're going to look at highlights the fact that many of linear ODEs that we've looked at that have had non-constant coefficients have had powers of t in their coefficient functions. And for that reason, we'd like to know how to take the Laplace transform of functions whose Laplace transform is known or presumed to be known, and then multiply it by a factor of t to the n. So here, what I want you to take from this is that multiplying by t to the n introduces derivatives in the S domain. So suppose f of t is piecewise continuous on a certain interval with exponential order. That just means that we can compute the Laplace transform. And then for any positive integer n, if we were to compute the Laplace transform of t to the n f of t, so similar to the last example, we're assuming we know this Laplace transform, or at least that we know that this Laplace transform exists. Based on that knowledge, what can we say about the function t to the n f of t? Meaning we take the function whose Laplace transform we know, we multiply it by t to the n for n a positive integer. And it turns out that this is equal to -1 to the n times the nth derivative with respect to s of the Laplace transform of f of t. So the first thing I want to point out is that notice here we've got the n as the power, and that shows up twice, or I guess I should say 3 times. I missed this in the first time, folks. So again, if we've got this n here, it shows up in 3 different locations in this theorem. And so we take -1 to whatever the power of that power function is. And again, we're assuming that n is a positive integer. And then we take as many derivatives as we have powers of t of the known Laplace transform. We can write that another way. We can write that as -1 to the n times dn dsn of just f of s. And so here you can see that we're taking the nth derivative with respect to s of this function here. So let's go ahead and give that a shot. In this case, we're asked to compute the Laplace transform of these 2 functions. I guess step 1 is we know the Laplace transform of the cosine of 5t is equal to s over s squared plus 25. So the question then becomes, what about the Laplace transform of t times the cosine of 5t? And so this is where we're going to incorporate the above formula that we'll prove in class. This is -1 to the +1 power, and we're going to take the first derivative of the known Laplace transform for cosine 5t. So one thing that could be a little bit confusing here, you don't need to annotate this, but here this is understood to be to the first power. That's why this was to the first power, and that's why I'm taking the first derivative of the Laplace transform of the cosine of 5t. So this is just -1, and then here I'm going to take a derivative using the quotient rule. So we've got the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function all over the bottom function squared. And we can clean this up. This cleans up to be -1 times, we'll have a minus s squared and then plus 25 all over s squared plus 25 squared. Distributing that -1 gives us s squared minus 25 all over s squared plus 25 squared. In practicality, folks, we may need to use some interesting inverse transforms, such as our convolution integrals here, or we might try partial fraction decomposition if we were going to try to convert this back. So the next one we want to look at is the Laplace transform of the second term, and we know that the Laplace transform of the sine of 3t, we know that is 3 over s squared plus 3 squared, or 9. So the question now becomes, what is the Laplace transform of t squared sine of 3t? Well, following this formula, this is going to be negative 1 to the second power, and it's the second power because this is t to the second power. Then we're going to take the second derivative with respect to s, both times, of our known Laplace transformation of the sine of 3t. So if we continue, this is just 1, and now we'll have to take two derivatives here. So I'll do that staggered. So as I take the derivative of the first, or so if I take the first derivative of this, I end up with minus 6s all over s squared plus 9 squared. If I did that too fast for you, just remember that you could rewrite this as 3s squared plus 9 to the negative 1 power. Take the derivative that way, and don't forget your chain rule. So now we need to take the second. We need to take one more derivative. Taking the second derivative of that original 3 over s squared plus 9, or taking the derivative of our result, will give us our final answer to this question. So here I'm going to have to use the product rule, or excuse me, the quotient rule again. So here's the bottom function, s squared plus 9 squared, times the derivative of the top function, which is minus 6, minus the top function, negative 6s, times the derivative of the bottom function. And that would be, and I've run out of room, folks, I'm sorry. The derivative of that bottom function would be 2 times s squared plus 9 to the first power times 2s by the chain rule, all over that bottom function, which was originally this squared, and when I square that again, that's the same as to the fourth power. That turns out, and you can check this, that this simplifies to be 18 times s squared minus 3 all over s squared plus 9 to the third power. You can see right off the bat that one of those powers will cancel, and that's how what remains cleans up. So folks, I didn't have enough room to give the full answer. Let's try to write it down here, I guess. So the Laplace transform of t cosine 5t plus t squared times the sine of 3t will just be this expression plus this expression, and you can copy that down here if you wish. So I'd like to continue, and we can see how else this can be helpful here. So here we've got a differential equation. In this case, it's a second order linear differential equation. But as per my first comment, notice that we don't have constant coefficient functions here. But never fear, that theorem tells us how we can still do the Laplace transform to this. And so if we were to take the Laplace transform normally, when we take the Laplace transform of y double prime, we would say that that is s squared y sub s minus s y sub 0 minus y prime of 0. That's assuming that y has a Laplace transform. And in our case, if we plug in our initial conditions, we would have minus just s and then minus 0, or s squared y sub s minus s, where I plugged in the initial conditions. But what we want to do now is we want to look at the Laplace transform of t y double prime. So if we go to look at the Laplace transform of t y double prime, that's going to be negative 1 to the first power. Remember, that's the first power because this is t to the first power, times the first derivative of s squared y sub s minus s. And so if we continue that, we get negative 1. And taking this derivative, well, careful, we're going to have to do a product rule here because we're differentiating with respect to s. So if we go to take that product rule, we'll have s squared y prime sub s, that's the first derivative second, plus the derivative first times the second. So all of that I've written so far is the product rule. And then minus 1 when we go to take the derivative of just s. We can clean that up. Let's do so. Minus s squared y prime of s minus 2s y sub s plus 1. Then let's go ahead and take the Laplace transform of just y prime. Well, the Laplace transform of y prime we know is s y sub s minus y sub 0, which in our case is s y sub s minus 1. There's nothing new about step 2. Step 3, though, is similar to step 1 in that I know the Laplace transform of just y we represent as we represent as capital Y sub s. So if I want to do the Laplace transform of t times y, we would have negative 1. Again, this will be to the first power, and we will take the first derivative of y sub s. Okay. If this had been a higher power of t, say t to the 5th power, then this would be minus 1 to the 5th power, and I'd be taking the 5th derivative of y sub s. So continuing, we end up with just negative 1 y prime of s. So if I put all this together, what we end up with is that the Laplace transform of the original ODE, together with those initial conditions, comes out to be minus s squared y prime of s minus 2s y sub s plus 1 plus s y sub s minus 1, and then minus y prime of s equals 0. If I continue to clean this up, I end up with minus s squared minus 1 y prime of s. The 1's cancel, and then I've got minus s y sub s equals 0. This is a separable first order ODE in the S domain. And it may not be clear, but that significantly eases our problem of trying to solve the original ODE. What I'd like to do is let's just finish this out. I could rewrite this as y prime of s is equal to s y sub s divided by, and we'll put the negative sign out front, s squared plus 1. Or if I continue, y prime of s is equal to minus s over s squared plus 1 y sub s. And here we can see that this ODE is certainly separable. And when we get to class, we'll go ahead and solve this ODE. So folks, that finishes up this video on how multiplying by t to the n introduces derivatives into the S domain. In some cases, we'll actually just take those derivatives. So for example, here, this introduced take the derivative of the Laplace transform of the cosine of 5t, and we did so and cleaned it up. In other cases, though, it introduces the derivatives more abstractly, in the sense that we started with a second-order linear ODE in the time domain that was not separable. And in this case, and this is not always the case, but in this case, when we applied the Laplace transform, we ended up with a new differential equation, but this new differential equation in this case was first order, and it was separable, which is far easier to solve than the original. So folks, I hope this video gave you a nice introduction to how we can create differential equations in the S domain. After this, we'll pick up with the step functions.